Good afternoon. I'm Andrew Christie from Sofant Technologies, and I'm going to talk about MEMS-based phased arrays. But before I, and I'm going to today I'm going to talk about technology and architectures. But before I talk about the technology and architectures, maybe I should just introduce Sofant briefly. We're an Edinburgh-based company. We've been developing, our core technology is RF MEMS. We've developed our own MEMS process and our own MEMS bridge. Our focus primarily at the moment is on the Ka band. So today I'm going to talk about Ka band phased arrays. And again, let me just jump into the presentation, but really I'm not talking about products. If you would like to see an example of what a product would look like, there is in the room behind us, there is a prototype of our terminal. I guess from a market perspective, everyone hears about Starlink. We're focused on Ka band, not Ku band, and we're focused on the performance end of the market. So where people are working between GEO, LEO, and MEO satellites, we're not focused primarily on LEO satellites. The requirements for LEOs are much simpler than multi-orbit applications. So the technology also, we're focused on Ka band today, but the technology is applicable across a broad range of applications looking at phase shifting and beam steering. Really, from our perspective, anything from X-band up is where our technology comes into its own. Hopefully by the end of the presentation, you'll understand what our benefits are and the architecture that we enable. So I'm going to, like I said, I'm going to focus very much on technology and architectures as a vehicle to describe what we're doing and how it's different from other solutions today. I'm going to compare our architecture. We enable a new architecture with the kind of the conventional approach that you see today. Most phased arrays in the market today are based on a conventional, mostly SOI solution, which is what I'm going to compare with. There are other solutions out there today, and I know there are people from other terminal companies here today who have alternative solutions. You'll see as I go through the presentation, the market that we're targeting, why I'm comparing against a conventional solution. Some of the other solutions have different advantages and benefits, but we're focused on a particular area of the market. So I'm going to start off with the comparison of architectures and some of the trade-offs from a technical perspective that you must address when you go to this alternative architecture. And then for anyone who's been involved with MEMS or heard about MEMS, it's a challenging technology to develop. There are many, many companies who have tried to develop MEMS and have either given up or have failed. And the classic reason is reliability. So I have a slide here which talks about reliability and how we've addressed that. I'll follow that with just some other examples, and some of the other presenters this morning have covered some of these topics and are much more expert on these topics than me, but would like to introduce and touch lightly on some of the other advantages that RF MEMS brings to the architecture. And then finally, I have some measurements of a real array. So you can see that it is working, it's real, it's not just a bunch of PowerPoint slides. Okay. So when we set out to develop phased arrays, we were trying to work out what the real benefits of RF MEMS could be to this area. And so we settled on this. What we got a lot of feedback from customers was these three parameters were the most important: size, weight, and power. So we set out to architect a system that could achieve the lowest size, weight, and power for these kind of Ka band multi-orbit systems. What MEMS enables is, and I'll talk about this a bit more in subsequent slides, is it has a much, much lower loss than conventional semiconductor approaches. And again, I've said this already, there's an alternative architecture we can enable here. And this is the big thing. With the combination of RF MEMS and GaN PAs, we get this significant power saving. So we're very aligned with the people this morning who've talked about our GaN PAs, the benefits of GaN PAs, some of the things you can do with it. We take RF MEMS, we combine it with GaN, and we get a significant performance improvement. So, oops, sorry. This is just an image showing one of our RF MEMS devices. You can see there's a number of IOs. I won't go into all the detail, but here's a very simplified block diagram. So it's quite a conventional solution in terms of what you get, functionality: 6 bits of phase shift, 3 bits of attenuation, And for the satellite space, you need an RF switch, which is switches between polarizations, depending which satellite you're working with. So this approach today, the way we approach it, we have a single MEMS device, and you'll see it later, driving a single antenna element. What I'm going to talk about later is a comparison with a conventional approach. The conventional approach has additional functionality, but they generally group more components into a single chip to drive multiple antennas. So we've gone intentionally with a less integration. And the reason we do that is because that means less loss, and I'll cover that later. So it's a very simple looking chip, but there's a reason why we haven't put more into the chip. So if we start talking about architectures, and again, I've said on the right-hand side, we have a conventional silicon approach. And here we have the Sofant approach. Now, the first thing to consider here is, I mentioned RF loss. When we've benchmarked a traditional typical phase shifter using an SOI or SIGI or similar type approach has about 5 to 7 dBs of loss for a similar number of equivalent number of bits, phase shifter bits, versus our approximately 2 dBs. So we've got this significant benefit. In a conventional architecture, because of this loss here, and when you add in an attenuator and a switch, what they do is they move the phase shifter and the attenuator in a conventional architecture before the PA. Because if you put it after the PA, this loss means this PA has to create a lot more power, and they're not very efficient. So what we're able to do in our architecture, and you can see this is an equivalent, so we're showing 16 antenna elements, same here, 16. So this is a module we make. This is a kind of a traditional approach. People make a module, it drops onto your motherboard. And normally they make 4 paths into a single chip, sometimes 8 paths into a single chip. We make a single device driving 1 antenna. The reason it's showing 2 antennas here is to demark that we've got RHCP and LHCP in this antenna. So you switch between them depending which satellite network you're operating on. So, I did it again. So what we do is we take the power amplifier off this assembly, and we have a single PA driving all 16 antenna elements. So this amplifier, it drives and it's distributed to each of the antennas versus having 16 amplifiers on a traditional approach. I'll come to this in the next slide and tell you, and we'll do a comparison of some of the trade-offs and what the benefits and disadvantages of both approaches are, but this is where we get the power saving benefit. I'll talk about some of the other benefits later, and just to remember, you see we have a DC-DC converter supplying the PA, so there's multiple levels of benefit you can get in these types of systems when you make this architectural change. So if we start talking about benefits and challenges, we can use a GaN PA. We get significantly higher efficiency. So from what we have been able to benchmark and baseline from papers and what's been published, what we see in data sheets, we're developing our own GaN PA, and so we can set high 30% efficiency PAEs possible. For a silicon-based solution, about 8% is about what you'll get out of it. For the kind of power levels you need to drive the antenna elements. The other things, and I'll touch on those a bit later, is we've now moved the PA off the subassembly, and it's now on our motherboard, so we can directly heat sink it to the chassis. So that helps us with thermal management. And there's some other benefits I'll talk about thermal management later. I'll talk about tapering and some of the other linearization techniques later, but we have the ability here to apply tapering at the PA, which again saves some power. The one thing that we have to be careful about is because we have a lot more post-PA loss than the conventional solution, we have to manage post-PA loss very carefully. And I'll talk about that in the next slide. So this is kind of a loss comparison. I have another slide after this which translates this into what the benefits in terms of power are, but just to compare the two architectures. So if we take the kind of the conventional approach, and I'm just zooming in on one antenna element, and this is one path of the conventional lineup, And the loss that we're talking about, the comparative loss, is the loss after the chip. So there's some loss feeding to the antenna elements. As I said before, the difference in these solutions, they typically have 4 paths combined into one chip. So they have a longer track to each of the antenna elements. In our case, because we put the MEMS as an individual component, it goes directly underneath the antenna, so we don't have that trace loss. So if you start doing a loss balance here, so if we take post-PA losses, conventional versus Sofant, we have some loss in the splitter and the tracking. So we're talking about the splitter here and the tracking through the lineup. We have the MEMS loss, and you can see here's a plot showing simulated versus measured loss for a phase shifter attenuator switch combo. So you can see the simulation up there. It's about 4 dBs loss. You can see we've put 4 dBs in here. So for the Sofant approach, we have about 6 dBs loss versus conventional where it's 0.6. And you say, okay, so we should lose, right? But I'm going to show you on the next slide that we don't lose, because when you start to look at the benefits of the increased PA efficiency, when you combine those two together, the MEMS, lower MEMS loss, the different architecture, and again PA, you win. So this architecture is actually superior in terms of power consumption. So sorry, this is it might be a little bit of a bit tough at this time of the day with all the numbers I've put on there, but I'll try to explain how we've done a comparative calculation for both architectures. Okay, so the key things here are, for the SatCom space, they don't talk about dBm, they talk about dBW, so it's EIRP, so it's effective radiated power, isotropic radiated power. So we've tried to make 2 solutions, one using a conventional approach, one using our approach, which both have the same EIRP. Remember, they've got different architectures, so and that's what this table here is showing, is how we calculate that comparison. Because we want to be like for like and how we determine like for like is this, we match EIRP. So you can see this shows the number of elements in the array, and this shows the output power at the antenna, or the power going to each individual antenna element. We've based this on commercially available ICs. Most of them can get to about plus 12 dBm output power. So that's where this number here came from. And then we've taken off 0.6 dB for post-PA loss, and we get to 11.4. For the Sofant approach, we set that at 12, because we can get much more power than this, but to make it fairly comparative. But we can make our array smaller because we can get a little bit more power out of our lineup. The way we get this power, and you can see this here, this is the PA power. So we've got one PA, a 30 dBm, 1 watt PA driving 16 antenna elements instead of these individual amplifiers. And then when you go down the rest of it, you say, okay, so that's the power that the amplifier is putting out in watts or milliwatts. This is a Sofant PA. You take the efficiency, and then you get these 2 numbers. So this is PDC, so the DC power going into the conventional array, and then the Sofant array. And then the other number, which we'll come back to later, which is very important, is the power dissipation. So not only is our power consumption much lower, but our power dissipation is much lower, which is significant when you're starting to try and think about thermal management and how to make this small and light. And you can see here, just in headline numbers, this is the kinds of reductions in both in power consumption and power dissipation we enable. I mentioned MEMS before. I mentioned reliability. So just to kind of pause on reliability, because we find there's lots of people who are skeptical about RF MEMS and how do you make it reliable. Traditionally, the structure of MEMS that we use, it's a capacitive MEMS. Charge-based stiction is traditionally the stumbling block. And the way this is evaluated and tested, you typically do 2 tests. You do a thing called a cycle test, and you do a hold down test. The cycle test is the more difficult, and the benchmark we've set ourselves, which is considered to be a high benchmark, is kind of the gold standard for MEMS, is 100 billion switching events. So what we do is we take a single MEMS bridge and we switch it 100 billion times on and off. And while we're doing that, we monitor the MEMS device. And how we do that, this curve shows this. So this is the capacitance. I mentioned before, it's a capacitive structure. So the capacitance changes between on and off. So this is the on capacitance. This is the off capacitance. This is the control. This is actually not, the value along here is just, it's point in the sample. It's not actually a voltage or anything like that. And what we're looking at is the actuation voltage for this device is about 40 volts. So in the middle here is about 40 volts. So this is turning it on and turning it off. We've overlaid all of those switching events on top of each other. And what you want to see is that they overlay nicely on top of each other. And you can see there's a small amount of variation. But what you would see if there was a problem with stiction is this on capacitance would start to reduce. And if the MEMS bridge is starting, its physical properties are starting to change, you'll see the shape of this curve will change and it might move left or right, and equally on the off cycle. So this is a classic way to evaluate MEMS reliability. So we've proven that they're reliable. We've gone well beyond 100 billion switching events. It takes some time, so we tend to stop at 100 billion, but we can consistently get parts through that reliability. So I'll touch just on this quickly because I think many of the PA people have talked about this and are much better equipped to discuss this than me. But we have some other benefits in this architecture. I mentioned before we have this DC to DC converter. So this allows us to do, when you're working in the SatCom space to manage side lobes, you have to taper. And what that means is, and this diagram here kind of demonstrates it, at the center of the array, you have the highest power. And as you go across the array towards the edges, you tend to reduce the power. And that's called tapering. And that allows you to manage the side lobes of the pattern. So this example here is showing how we taper. What we do is we adjust the DC voltage, the drain voltage to the PA across the array. So at the center, we might, for example, have, just pick a number, 12 volts. And as we go across the edge, we'll reduce the drain voltage down to maybe 4 volts at the very edge. And what that means is because the PA needs to put out less power at the edges, we can still have the PA running efficiently at the edges. So normally what people would do is they'd reduce the input level to the PA. It would still have the same voltage. It'd still be dissipating the same bias current, DC power. But in this way, we can get an additional benefit in terms of power saving. On top of that, we can do some of the things that I think Chris was talking about earlier. We've got options to do PI linearization, because in a normal architecture, it's difficult to do that because you don't have space close to the parts. Because we've got one PA driving 16, we've got more space to implement things like linearization. We can do average power tracking. In theory, we could do envelope tracking if we needed it. This is important as we move forward because the satellite community is starting to look at using 5GPP modulation formats, and the non-terrestrial network standards are starting to drive the requirements for higher linearity. If you don't start looking at linearization, you may have to back off the solution. It gets less efficient. So we think this gives a roadmap to support higher order modulation, more complex modulation moving forward. Passive cooling, I said before, we looked at the comparison between our approach and conventional. We've extensively modeled this, and we can passively cool the array. So this simulation is showing, this is the motherboard. The antenna module sits on top. The PA is here. The up converter is here. And this is a mirror of a PA up converter. We've got all of the heat sources on the board. And we've shown through simulation that we can, using passive cooling, and this is a fairly rudimentary heatsink design, but it's 60 millimeters long. So it's quite compact. In this industry, it's quite compact. We can maintain a maximum temperature of 110 degrees C. So people were talking about PA reliability. We can easily keep it within a safe range, and we can easily keep the rest of the electronics in a safe range in any environment. So this means this is a big weight saving as well. But also people don't want to use fans. So there's two benefits here. There's a reliability issue for the PA. There's a reliability issue not having to have moving parts, and then there's a weight saving. My final slide, this is showing measurements. So this was taken recently, again, Ka band, and this plot is showing, this isn't for a full-size array. Last week we measured the full-size array, but we haven't post-processed all of the data yet. So this is 4 elements by 16 elements. So I'm taking it in the principal plane of the 16 elements. If you took a 90-degree cut, it would have a more fan-shaped beam. But you can see here, this is boresight, and then we're stepping across in both directions out to about plus 70. So we can scan plus or minus 70 degrees. So so this is the whole lineup, the whole architecture. So I think, from our perspective, we've had a number of years of technology development. Now we have a full system working and demonstratable. So thank you very much. Any questions?
Yeah, thank you very much, Andrew. Any questions?
Hi, Alexander Shalavi from CADFIM. Thank you for the presentation, and I have 2 questions.
Sure.
First one is, what's the technology for the RF MEMS itself? Is it made on silicon or GaN?
It's on silicon. It's on high-res silicon.
Okay.
So inherently it's a low-cost process.
And do you do it? Do you have like a fab somewhere?
We're fabless. We use a European fab. So it's our process, our bridge design, but running in a commercial fab.
Okay. And the second point, maybe I was confused. I didn't understand what's the difference between like your architecture and the MEMS. So if you take your architecture but with another switch, like a PR.
So the reason you couldn't use another switch is the loss budget would go up. So where I showed, if I go back, the loss budget, the key is this number here. It's 40 Bs. That's for 40 Bs is for a 6-bit phase shifter, a 3-bit attenuator, and a switch. If you took conventional approach, just the phase shifter is 5 to 7 dBs, and then you add on the attenuator and the switch, and it's more. So it would be north of 10 dBs. But I don't know what I'd have to figure out, but it's significantly more, and that architecture falls over at that point because these post-PA losses would become so high that they would negate the benefit of having the GaN PA.
Okay.
So does that answer your question?
Yeah.
Okay.
Thank you.
Okay, over there.
Thank you very much. Hasha from MediaTek. So I have 2 questions again. One of them is how fast you can switch.
The current switch is about a microsecond.
Okay, so FR1 is okay for FR1, basically, neurology.
Yep.
Okay. And the second question, if someone says for silicon PA, I can give you 10%, 15%, 16% efficiency, which we have in the market. So would you choose 1:16, or you will change the ratio, or what would you do?
You have an option. You could change the ratio. I mean, we set the ratio because it was a nice mix, a nice blend. But you're right. You could reduce the number of. You could put one PA per 8 PA, one PA per 8 antenna elements, or you can play around with that number. We've set it on an architecture and scaled out designs and everything based on 1:16, but it's not fixed.
I think this architecture for the DPD point of view is one of the best. I mean, you can do it easily in a phase array, which usually we cannot do.
Yes. Okay. Thank you very much.
Yep.
Hi, Andrew. Andy Crofts from Qorvo.
Andy.
You talked a lot about the transmitter, but what happens on the receiver side? Is
So
there an LNA?
Yeah, I didn't talk about the receive side because we're very pragmatic. We don't use MEMS on receive, and the reason we don't use MEMS on receive is but we do something different on receive than most other people do. Because you want the LNA, as I think you're alluding to, close to the antenna element. Yeah. For the same reason that we want on transmit, we want it right beside the antenna element. So we use a conventional LNA, but it's of our own design because we played some tricks in the LNA to reduce the loss before the LNA, so within the chip, so we can get the highest possible noise figure. And so we actually we think our receive lineup is lower power and smaller size than what's on the market today because we've got lower effective noise figure in our LNA.
Okay. If you want a beamformer, I'm open anytime.
Thanks.
Okay, there was one more question over there, I think.
Thank you for the presentation. Very interesting. I'm Taj from Space Networks.
Yes.
The question I have is the power spectral density for these.
Mhm.
It's very stringent with the satellite network operators.
Mhm.
So
We work with one of the satellite operators,
Right.
and we've modeled that extensively, and we can meet the power. There's no issue with meeting power
there are no
spectral density.
issues. Okay.
Yeah.
Oh,
Mhm.
thank you.
Yeah, it's a good question, but yeah, it's a tricky one. It's a tricky problem. We struggled with it for a while, but we worked it out. So
Sure.
yeah.
All right. Thank you.
Yeah, just one last one before we break for coffee.
Hi again, me, Dr. Azim from Electronics. So my question is, now you have taken the amplifiers out of the switch and then replaced them with a one amplifier, which makes the architecture a lot more simpler compared to the conventional one.
Yes.
So in terms of the cost, how your product compares with the conventional switches? Do we see a significant drop off or high?
We've done some price benchmarking, and we think it can be equivalent to a conventional approach in terms of cost. The GaN PA is quite small. One of the nice things about GaN is the earlier presenters have presented is it's can have quite high current density, so you can make the die very small. So you don't pay you don't pay a penalty in terms of cost. We have a less integrated solution. That's true, but so there might be a small difference in assembly cost, but otherwise from a component cost compare with conventional, it's equivalent.
All right, thank you.
Oh, yeah, okay, just one more then.
Yeah, a quick question. Are the switches affected by the power of the signal?
No, the MEMS is very, very linear. In fact, it's very difficult to measure the linearity because that's actually one of the inherent advantages. So we've designed the current MEMS bridges for a certain power level, but we've looked at much, much higher power level devices, so they're not affected by it. The thing you have to worry about is if you don't design them correctly, you can get RF self-actuation. That's probably the biggest issue. But in terms of linearization or linear performance, they're extremely
Yeah, in
linear.
terms of actuation, yeah. And in terms of the environment, I mean, do they operate in different environment?
So if you look back at the picture, I mean, this is classic MEMS. You can see it's a packaged device. So this is a silicon die, and this is a glass cap. It's a low cost hermetically sealed package. Because moisture can be a problem for MEMS. Other than that, we've measured them over temperature. There's no problem. The bridge is designed so it's consistent over -40 to +105. So it's robust.
Yeah. I don't know if this has already been mentioned. What about vibration?
Well, yeah. When you look at the MEMS bridge, it's tiny. The mass is so low that it's not subject to issues with vibration.
Good.
So yeah.
Okay, thanks.